Okay, so for the moment we have seen some basics of state chart modeling through the Stateflow tool. So we have seen that it is possible to define states, it is possible to define transitions. Now we have to move forward, we have to do some more modeling to specify additional details into this model. In particular, we can define actions to be performed when the system is entering or is staying or it is exiting from a given state. And we can specify the rationale with which we decide or not to take a transition. So let's imagine we want to specify some action to be performed when we are in a given state. For the moment, we haven't specified nothing other than just the fact that the item is able to switch between two states. But we haven't given any specific meaning to these states. Let's imagine this very simple chart is intended for taking the control of an output, so that we want to generate a square waveform on this output. Let's imagine that the two states corresponds to the working state of a lamp. When disabled, the lamp is off. When enabled, the lamp is on. So we have to find a way for conveying in the model the behavior that we just mentioned. So we want to say that when we are in the disabled state, the lamp that is controlled by this state chart shall stay to off. So here we can populate the state by adding actions to be performed. These actions can be performed in different instants of time associated with the model entering, staying on, or exiting from this state. If you look into the description of the state chart language, you will see that you can specify action when entering a state, during the stay in a given state, or right at the exiting of the state. This can be done through these labels. EN double columns stands for entering. So what is following this label is the set of actions to perform when entering the state. DU is a label that states that the following actions have to be performed as long as we stay in this state. EX is the label that we use to specify that the actions that follows have to be performed before exiting the state. Okay? So, let's imagine that we want to say that the lamp shall stay off when we enter in this state. So we can start typing something like this. So lamp is an object that we use to refer to the physical object lamp, and we want to say the lamp is set to 0 when entering in this disabled state. Similarly, in the enabled state, we can say that when entering, we want to set lamp to 1. So the state chart modeling allows you to insert within the state actions in the form of C statements. So we can decide to have a certain element of our model that is an object that we call lamp, and we can decide that we want to assign a given value to this lamp. The value can be a constant, can be also the result of a computation coming from the invocation of a function. For the moment, let me just say that lamp is 0 and lamp is 1. Let's see what happens when we try to simulate this. Well, you have to imagine that the action performed by Simulink when asking to simulate this state chart is first to translate this state chart into C code, then to compile the code, then to link the code with the simulator, and eventually invoking the solver to advance the simulation. Okay? Being our model now using an object that is called lamp, the result in C code will have a variable called lamp that is subject to assignment. It is clearly that as we haven't yet defined lamp, we just instantiated lamp and used lamp. When the compiler works, it gives you an error. There is an undefined object. Indeed, the simulation gives you an error. This is the result of the preparation steps for the simulation. And the result is that we have an unresolved symbol found in top state flow. This symbol is lamp. In order to solve this problem and allows the simulation to advance, you have to define what lamp is. The compiler is smart enough to suggest you what to do. Indeed, you can see here the name of the object, lamp. Then you have the possibility of specifying which is the class for this object. Is this an object that is intended for storing a value? So it has to be dealt as a piece of data. Is this an object intended for notifying that something happens, but it is not intended for retaining any data? So in this case is an event. Is this something that is used to communicate with something else? So is this a message? So this is the class of the object. For the moment, we stay with data. So to specify that lamp is an object intended for storing values. Then to each object, we can associate a scope that is a sort of visibility. Is the object something intended for getting data from the input? So it is something intended for acquiring something from other subsystems from the plant to provide something to the stateflow to work with. In that case, the object will be an input. Is this object something to convey a value outside the stateflow to the plant or to other subsystems of our schematic? In that case, it is an output. The object can be also local. This means that it is something intended for storing data, but that is not appearing on the interfaces of the state chart. It is like a local variable to a C function. It is something that is used within the function So in this case, it is something that is used within the state flow, but nobody else will be able to see that value because it is not propagating outside the state flow. We can have a constant that is a local object that is associated with a value that is not going to change during the execution of the state flow. It can be a parameter. This is a kind of, let me say, a define that is something that is associated with a value that is not going to change throughout the code, but that you can modify from the outside of your model by tuning that parameter. Or it can be data stored memory. This is something more advanced we will see later on. So let's say that LAMP is a class data scope output. We can type OK. You can see that the Model Explorer is opened. The Model Explorer is the place where you can find all the objects defined in your model. You can see that for our state chart that we call the top state flow, we have an object LAMP of scope output. Then you can insert additional parameters to better quantify the properties of this object. For example, you can select the data type. Here we say that we inherit this from Simulink. In other cases, we could have the need for being more specific. So we can specify one of the data types out of the native data types supported by Simulink. For the moment, let me say that it is same as Simulink. So if we go back to the top level, we see that we have a new connector that has been added to the side of the state flow. You can see here LAMP, and then there is the exit arrow. This is because we created the LAMP object with scope output. So this is something that is intended to propagate a value outside the state flow. So being this a component out of the Simulink library, this is something that should appear on the schematic as any output of any Simulink blocks. So we can have here the connector. So we can decide that we can take a scope that we drag here. We can connect the two. So we can use this scope to display what is happening on the LAMP output. If we do the simulation, we can see that we have our LAMP output that is switching from 1 to 0 and from 0 to 1, representing the behavior that we have here. We can do the simulation step by step. You can see that at time 0, we are here, LAMP is set to 0. We do one step, and we are here. We can even zoom. You can see that we started from 0. We remain to 0 for one step cycle. Then at 0.1 seconds, we have the ramp from 0 to 1. Then if we advance the simulation, let me see. Okay, here. If we advance the simulation, we can see that we have the state transition, and each time we have a transition, the output is modified. Okay? So basically, here we are able to generate the square waveform as we like. Okay? Then, if we analyze the timeline of our model, we can see that each transition is taken at every iteration, at every integration step. So the output stays to 0 for 100 milliseconds, then we take the state transition, it stays to 1 for 100 milliseconds, and so on and so forth. You can easily recognize this by zooming a little bit here. Let me see if I'm able to do that. You can see that here, oh, this is not very visible. Anyway, this is 0.2, this is 0.3. This means that our model is updated every 100 milliseconds. This is exactly what we specified when we selected the solver. So we have a square waveform with a period of 200 milliseconds. This is not always the case. We may want to have something different. Let's say that we have to stay 0 for half a second, and then we want to go 1 and stay 1 for half a second. So we want to be able to further refine our model by specifying some properties associated with the transition. Let's say we want to stay here, we want to remain here for half a second. So I want to take this transition only after half a second I am spending in this disabled state. Okay? So this means that we could have the need for adding some properties to the transition. If you tab on the transition, you can see that there is a question mark here. This question mark is the placeholder for the enabling transition. So, sorry, for the enabling condition. Each transition can be associated with an enabling condition. The enabling condition is evaluated by the solver, and if true, the transition is taken. If there are no condition on the transition is always enabled. Okay? So, by starting typing something here, we can specify which is the enabling condition. If you look into the state chart manual, you can find that there are many possible ways of specifying enabling conditions. Enabling condition can be regulated by Boolean conditions, so the very same way you write a piece of C code. You can write here a Boolean condition. So you can have an input, then you can check whether the input is equal to a certain value, greater than, less than, whatever. You can do complex Boolean conditions that are a combination of different statements, and then you can use the traditional logic operators like or, and, to combine properly all these conditions. Well, this is nothing special, it is like in C code. What you can do here is to also specify an enabling condition that is related to time. And you can use a combination of enabling condition based on time and Boolean conditions. So this gives you a lot of power. For example, you can say, I want to transit on this transition after 0.5 second. After is a keyword of the Stateflow tool that is intended for specifying that the transition associated with this condition is enabled half a second after we entered in the state from which the transition originates. So after 0.5 second means state flow, enter in the disabled state, start a clock timer programmed for half a second. When an half a second is over, the transition is enabled. And so you can traverse it. We can see this through the step-by-step simulation. So we start, sorry, this is second. So S is not known, sec is known, sec is seconds. So we start, we enter in the disabled state because this is the default state. Then look at the timeline here, it is 0. Look what is happening. We are advancing the simulation, the time is elapsing, but we are not moving out of this. This is because the transition that is bringing the execution out of disabled into enabled is associated with this enabling condition. And this enabling condition is based on a temporal logic. The temporal logic says that half a second is the limit. We have to wait for half a second. Indeed, t is 0.4, and we are still here. The next cycle, half a second is elapsed since we entered in the disabled, and so we can move to enabled. And you can see this in the timeline. It is maybe difficult to read this, but we are in between 0 and 1, so this is half a second. At half a second, we did the transition. Now, what is happening here? So this transition from enabled to disabled is not associated to any enabling condition. This means that by default, the transition is enabled. So we stay in the enabled state for just one simulation step. Indeed, here we are, back into the disabled state. And if we go ahead like this, we will see that we have this behavior. Indeed, we specified that we want to stay in the in the state, the disabled state for half a second. Then we move to enable and then we go back. If we want to have something that is symmetric, we can say this as well. Then let me move this side so it is more visible. We do the simulation again. Well, this time we have a 50% duty cycle. This is because the outgoing transition from enabled to disabled is again associated with a temporal condition. Okay? Is this clear? Were you able to simulate the same model? Okay. So, given a state, you can have multiple outgoing transitions. So you can have different paths that can bring the execution towards other states. So it is possible, for example, that there is a condition that states that we must remain in this state even if half a second is elapsed. Let's imagine that we want to have a switch to turn on the blinking or keep off the blinking. So this is an input that enables the operation of our system. Okay? If the new input that we haven't yet specified is 0, we stay disabled. If the input becomes 1, we do the blinking. So what we can have here, for example, we can have a self loop like this one with the condition enable equal to 0. So this is the way through which we can specify Boolean condition. Enable is a new object that I will assign an input scope, and enable is the name that I decided to give to my switch to enable the operation of this. When enable is 0, I stay disabled. When enable is 1, after half a second, I move from disabled to enabled. You can see that the Boolean condition must be typed in between squared brackets. So enable equal to 0. This is C code. Is like writing if enable equal 0. Okay. Then you can see that the Boolean conditions can be combined with temporal logic. So this shall be read as after half a second you enter disabled. If enable is 1, go ahead. Okay. So having enable to 1 is not enough for traversing this transition. We have to wait for half a second. Okay? Is this clear? Then, here you have to be very careful because otherwise things can become very, very nasty. Look at what we have here. We have two transitions that are originated from the same state. Okay? If the two transitions are regulated by enabling conditions that are not complementary, I mean, if both are enabled at the same time, well, you have troubles because the execution path should proceed towards two different directions. Let's imagine that we made a wrong model, so we enable both this transition and this one. So the solver, what has to do? Has the solver to bring the execution at the same time in disabled and enabled, or is the execution brought only to disabled or only to enabled? This is a source of non-determinism. At any given time, for the moment, we could have the machine in one state only. So it is not possible for the moment that our machine is concurrently in the disabled and the enabled state. So when you specify a condition, you have to be very careful. Otherwise, you can have unintended behaviors. Well, you have seen that once we inserted here a new transition, a number appeared on all the transitions originated from the same state. You see, we have 1, then you have 2. What is the meaning of this? This number here specifies the evaluation order. What does it mean? Once the solver needs to decide which transition to take, it sequentially evaluates the conditions associated with the different transitions according to this sequence number. So this is evaluated first, then this is evaluated. Okay? So the first transition that is enabled, it is taken. This means that if both 1 and 2 are enabled at the same time, as 1 is evaluated first, that is the transition that will be taken. Okay? This is a way for avoiding non-determinism. But be careful, there is a downside of this. If the transitions that you specify, the conditions that you specified here are not mutually exclusive, then you can have problems, because if in your intention one transition shall be taken instead of the other one, and then this is not happening, you have to remember the sequence order that you have here to motivate the behavior that you are observing. It's quite complex. Probably it is better if you model in such a way that transitions are regulated by conditions that are mutually exclusive. So it is not possible that two transitions are active at the same time. Okay? So here we have after alpha second we enter enable. If we enter enabled, if enable is 1, otherwise we stay here. What we do in the enable case? Well, so far we said we stay here for alpha second, and then we move to disabled. But what happens if in this alpha second we disable the behavior? So let me do this. Let me try to simulate. We will have an error because the enable is not defined yet. We define it. Then we go up. You can see that there is this enable input that appeared. Let me put here a constant. So now let's do the simulation again. You can see that the behavior is exactly the one that we have seen before. Let me now set this to 0. Then we do the simulation again. Well, the output will remain 0 no matter what, because we set the enable to 0. If we enter here, we can see that we remain in this state because the transition that is enabled is this one. Okay? Then let's do this. Let's set this to 1. Let's advance the simulation. We see that as we turned on the system, so we set enable to 1, now the system is operating. Then let's imagine that we want to keep this operating for a while. Then now we are in this state and we want to disable the machine. So again, we type 0. So look what is happening. The machine is insensitive to the changing in the enable signal, because when we are in this state, we have no transition that takes into consideration enable. Okay? When we enter here, we stay here for half a second, no matter what is happening into the enable signal. Then if the enable goes to 0, we have to wait till we exit from this transition to disable everything. Okay? Is this clear? Well, we can do something better. We can say, let's exit from here if enable is 0. Maybe we can try to refactor this. So here we added a new transition. This new transition is in alternative to the one regulated by a temporal logic. So when we are in enabled, we can go to disabled based on two conditions, either after half a second or as soon as enabled becomes 0. Here we do not have an issue of non-determinism because the two transitions are going towards the same state. So once we are in enabled, we always go to disabled. We can go there based on two possible scenarios, whether the machine is enabled and half a second is elapsed, or the machine is disabled. We can see this through this example. If we go back to 1 here, then we start the operations. So we go in the normal fashion. Then let's imagine we are now on. This is the first time step where we are on. We set this to 0. And we immediately go back to the disabled state. Okay? So transitions can be combined to obtain multiple effects. We can have mutually exclusive transitions, as in this case, or we can have transitions that have combined effects. So basically this is an if then else, this is an or, okay? So when I am in the enabled state, I can go to the disabled state either if I am here for half a second or if enabled goes to 0. So this means that I am able to go to the disabled state even if we are not yet in this enabled state for half a second. I can transition before. In this other case here, I can go from disabled to enabled only if enable is 1 and half a second is elapsed. Okay? Is this clear? You can see the difference. Then, what happens if we are in a state and none of the outgoing transition is enabled? We stay in the state. We do not do any state transition. Okay? Is this clear? Okay. So, let me take a copy of this and let me create a new model. So we are back here. Now let me do something different. Let's imagine that we want to perform some more complex operation other than just making some assignment to values or creating Boolean condition. let's assume that we want to do computations. For example, we want to count how many times we remained in the disabled state and how many times we remained in the enabled state. So we want to do some processing when we are in a given state. Here we can add to our state an action to be performed during the staying in the state. And this action can be something like the counter equal the counter plus 1, while the counter stays there. Similarly, when we are here in the enable state, I can say during the state I want to do enable counter equal enable counter plus 1. So I can type C statement in our model, and these C statements can be in the form of variable equal to a complex expression. For example, an increment like in this case. Okay. Then let's see what happens if we want to simulate this. Well, we have again an error because D counter and E counter are new. We haven't found them yet in our model. Again, here we have a suggestion. Let's see, what do we do with these objects, what they are? Well, the compiler suggests for them to be local. So we type OK. Then let's try to simulate again. We got an error. What is this error saying? Well, the error is saying that in our model, we are willing to use the counter with an assignment that takes the current value of the counter and increments it by 1. So we do not have an initial value for the counter. This is a problem. Where does the count start from? Okay, we have to be able to specify the initial value for this. Well, this can be done in different ways. We can do this, for example, when entering in the state. Here we can say the counter equal to 0. And we can say also here E counter equal to 0. So we can simulate. Now everything is fine. There is an initial value for the counter. This is set to 0 while we enter in the state. Then, as long as we stay in the state, right, this is not working properly because we are expecting for the counter to be incremented while we stay in the state. Okay, but look what is happening. We have a transition that goes out of the state and re-enter in the state. So we never stay in the state. We always go out and come back in. Okay? You see the point? Here I have an action that shall be executed during the staying in the state. But I never stay in the state because if enable is 0, I am using this loop. So I am exiting from the state and re-entering in the state. So I'm always executing the entry actions. We never execute the during action. Okay? You see the point? So we can do this because that loop is redundant. If we are enabled and we elapsed half a second since entering disabled, we go here, otherwise we stay there. So the loop enable equal to 0 is redundant. So let's see what happens now. We start, we set the counter to 0, we step, and this time the counter is 1. You can see there, because no transition is enabled. So the execution remains in the disabled state. So at each step, all the action under the during clause are executed. So for example, we can see that the counter is incremented, and as enable is set to 0, we always stay here and the counter increments. If we go to the constant, we set it to 1, and then we entered here already after half a second, so we can exit. We can see that the counter reached 13. Now we enter here, the counter becomes 0, and this is incremented as long as we stay in the state. Then we moved here, and the counter starts counting, okay? The point is that whenever we enter in this state, we execute enable. And so these two counters are set to 0, okay? So every time we transition, we reset the counter. Now, let's imagine we want to do something different. Let's imagine we want to keep the value of the counter for all the execution of the model. So I want to be able to count during the whole simulation how long I remained in the disabled state and how long I remained in the enabled state. Okay? Well, where is the problem and which is the solution? Any comment, any suggestion? Yoo-hoo, are you there? So let's think about the problem. We want to have the counter and enable counter the capability of accumulating the number of times we remained in disabled and enabled during the whole simulation, okay? So the counter equal to the counter plus 1 and e counter equal e counter plus 1 are okay. They are able to accumulate. The problem is that as we set to 0, as we set 0 into the counter and e counter, anytime we enter the corresponding state, we restart computing. So we need to do something different. We need to avoid setting 0 here and 0 here. We have to do the initialization in some other way. This is because if we do not do the initialization when entering the state, the value of the counter is preserved. Okay? So we need to initialize them somewhere else. Where? Well, we have two options. We can add a state that is the new default state that is intended only for initializing the counter and the counter. Then we move out of that and we will never enter there again. Or we can do the initialization as action associated to the transition. This is something that we haven't seen yet. Okay. The enabling condition on the transitions can be enriched with actions to be performed when traversing the transition. So the behavior that you can specify can be very complex. In parentheses, you can specify actions to be performed when traversing the transition. So with this action, we say, when traversing the default transition, set the counter and the counter to 0. This is done once at the beginning of the operations. Then it is never performed again. So the counter and the counter has a default value, 0. This value is not changed during the state transition that takes place in between disabled and disabled. The value is modified only during the stay in the specific state. In this way, if we save, we have this enabled, and we simulate again. Maybe, okay. You see, we enter in the default state with the two counters set to 0. Then we start running. The counter, when we are back inside the disabled state, is 4. So what we had the first time we left the disabled state. And so we can resume counting starting from 4. Okay? So what we have seen so far is the possibility of associating to states some actions that can be implemented in different moments in time, whether we enter in the state or during the stay in the state. Then we have seen that we can have transitions. Then we can have enabling conditions among the transitions, on the transition, sorry. Each enabling condition can be based on timing, Boolean conditions, a combination of the two, and then we can even specify actions to be performed when taking the transition. The meaning that we have here is the condition that enables this default transition is don't care. So the transition is always enabled when turning on the system. The action to be performed is the following. We can make this condition more complex, for example, by typing something in between parentheses here. So we can write here an action to be taken when this transition is traversed. Okay? Is this clear? Okay. So maybe it's worth to have another short break now, and then I want to look into the code that is generated starting from the models that we drawn this morning. Okay.